Hello, how's it going? Welcome to the final chapter, for now, in the OpenGL C++ series. Early graphics cards were heavily geared towards a very fixed way of working. Everything, even the lighting calculations, was fine-tuned and implemented on specialized hardware. However, that really is not the way modern graphics cards work. Modern graphics cards are highly parallel machines, and that's it. There's nothing inherently 3D about a modern graphics card. It just eats data, churns that data in a very parallel fashion, and spits out some stuff. And compute shaders are the logical conclusion of that through path. So let's say you have some sort of job, and the job is highly parallelizable. That is, it's a really simple job that you're doing a whole bunch of times. Then you might want to look at a compute shader. It's even better if that job, if the problem domain of that job can sort of be expressed in a spatial sense. So for instance, let's say that you have an array of objects, and for each object you need to calculate its model transform, or you need to shift a position by a velocity, or just something where you have a whole bunch of objects, you're working on them one at a time. This is a one-dimensional problem domain. Let's say, on the other hand, you have an image, and for every pixel in the image, you want to do some custom calculation to work out the value of that pixel. Or, alternatively, let's say you have a patch of space in parameter space, so in UV coordinates, and you want to calculate the height of every point there, or you want to evaluate some sort of function like a Bezier patch or something. Again, that's a highly parallelizable problem with a two-dimensional domain space, you could say. Let's say, on the other hand, you have a region of space and you want to calculate intersections with an iso surface in order to do like cube marching or something. Well, then you have a three-dimensional problem space, and compute shaders will actually handle all of these, and it does it pretty well. But in order to really understand what's happening, we need to take advantage of work group size. So when I run a compute shader, I have a little shader that does its job for each little invocation, each little step of my problem. But in addition to that, I have certain ways of partitioning my problem set. Let's say, for instance, that we have 256 objects that we need to modify with the compute shader. And these objects are all laid out in an array, but my compute shader has what's called a work group size. So I'll just grab some of that. We'll have a work group size. Usually I go with 64, okay? Because my NVIDIA, okay, this is sort of a long intro, but NVIDIA GPUs have a work group size of 32. That means that you can invoke 32 of these little shaders at the same time in a work group. AMD GPUs, on the other hand, have a work group size of 64, and provided you're not doing anything too funky, if your work group size is 32, you can get away with launching 64 threads at once. It's sort of okay. So every time the compute shader invokes a work group, it's actually invoking 64 of these elements at the same time. So as well as a work group size, we have a work group, which in this case, we're really just going in one dimension, so we have just the x. So 256 divided by 64, if I'm doing my math correctly, that would be 4 work groups in the x dimension, and then the default would be 1 work group in the y and z. So again, if I have my little shader, here's my shader source code, compile my shader, there it is. That is run in batches of, in 4 batches, where every batch is 64 threads working in parallel. Now, I have not been able to find a clear answer on the nature to which all of this is parallelized, in other words, the workgroups themselves. My understanding, the best of my understanding at the moment, is that these could potentially be invoked in parallel, but at the very least, we should not rely on the order of execution. I'll say that. Now, on the other hand, let's say we have, let's go with, just for simplicity, 256 by 256 as the size of a two-dimensional problem. And if I'm going with a workgroup size of 64 threads, and I want to distribute that evenly in both dimensions, that would be 8 by 8, and it doesn't have a Z dimension. So we have a workgroup size of 8 by 8, so we go invoke some little 2D tile, 2D square of our parameter space. We would then have a workgroup count of, I want to say, 32 lots of 8 is 256, so 32 workgroups in each dimension. We're not looking at Z, and so we would actually have 32 by 32, 1024 workgroups. Each workgroup is really running 8 threads at the same, 64 threads at the same time. So similarly, let's say we have 256, 256, 256. So some 3D problem with a 3D problem domain. Then we'll have a workgroup size of, we go cubed root of 64 is 4. And then a count of, I want to say, 64 workgroups in the X dimension, 64 in the Y dimension, and 64 in the Z dimension. And as always, when it comes to working with your problem, it's probably worth experimenting and just seeing which size and workgroup count is best. Modifying these parameters can make a significant difference. Let's get into the code. Right, so here we are in the code. I'm not going to go super in-depth in it. If I've done my job correctly through the series so far, you should be confident to jump into the code, look through it. But basically what we've got is I've got a window with a texture that I'm going to render to, and then just like in the post-processing video, I'm going to then render that texture onto the screen directly. And I've kept the camera around, but I've removed everything else. So if we run this, we've currently got a completely black screen because our texture is completely, like nothing's been done with our texture. So what I'm going to do is I'm going to write a compute shader which will clear the screen, write a color, a solid color to the screen. So I'll just open up my shaders folder and I'll make a new file. I'll call this ray tracer. And now let's jump in here. So this is going to be a compute shader. First thing we'll do is specify the language version. Compute shaders need to be OpenGL 4.3 at least. If you're following along with Mac, unfortunately, Mac does not follow OpenGL to the point where compute shaders were introduced. The next thing I'll do is I will specify the workgroup size, and that's done with this local size X. This is a two-dimensional problem, so I'll just specify X and Y. You can specify Z if you want, but if we don't put anything, the default will be 1 anyway. Then next up, I'm going to specify my resource that I'm binding with it, which is the texture that I'm going to write to. So I'll go layout, and for the format, RGB A32 floating point, binding, index will be 0. Now there's a slight difference here. Previously, we were using like sampler 2D. Now remember, a sampler is sort of a combined image sampler. So it's the texture that we're working with, and it's also the sampling parameters or program or whatever. But in this case, compute shaders are very explicit. I am not going to be sampling. We'll be doing per pixel access, and for that reason, we'll be using an image 2D. Now it's totally fine that we created a texture and then bound it as an image or a sampler. Both of those are fine. Just one thing I realized is I'm going to need to go to my texture factory, and where I created that image, Yep, that color buffer, I'm actually going to change that format to 32 float. Now the reason I'm doing that is that I want to write floating point data. Let's start our program. Now there are two stages. First stage is, I guess, orient ourselves and then write. So the goal will be to write every pixel on the screen. However, I'm going to break that down because this is a massively parallel job, and this shader will just be responsible for writing a single pixel. So that's what I mean when I say orient ourselves. So we need to work out which region of the color buffer this thing represents. So make an integer vector 2. Okay, so this global invocation ID refers to the global location of this specific invocation of the compute shader within the problem space. It's three-dimensional, so I need to extract the x and y components, and it's an unsigned vector, so we'll just convert it to an integer vector. So I'm going to work out read back the size of the image that I'm working with, and the reason for that is that I want to do a bounds check to check that this compute shader invocation is within range for the image. Because it could be, for instance, because we are going to be launching these several at a time with a non-one workgroup size, if that makes sense, it could be possible that we launch a workgroup where some invocations within that workgroup are covering the screen and some are just going to be off screen. Totally fine. When we launch a workgroup, that workgroup will complete when all invocations in that workgroup are complete. So if you imagine, let's say we have 8 invocations and 2 of them are doing actual work, the other 6 of them have just returned immediately. That's totally fine. A little bit wasteful, but what can you do? They will sit there and wait until the work is done, and then that work group will be complete. All right, so now we're going to write a pixel. So we will store into the image at this pixel position, and I'm just going to make something up. So we'll make a vec4. There we go. I'm really not too fussed about that. Just a random thing. Okay, great. So that is my compute shader. It will write a pixel at a time. We invoke it to run over the whole screen. The screen gets cleared. So then the question is, how do we sort of make that? So what I'll do is I'll just go down to View, and if we look in the shader header, we have this make module and this make shader. Now this make shader expects a vertex and fragment file path, and it uses this helper function make module. And I'm actually just gonna modify this. This will just be a quick hack. There are definitely more elegant ways to do this, but this will work for now. So I'll make a compute shader, and we will just need a single file path. And I will go into the source file and modify that make shader function. Sort of a big one here. Okay, so grab all of this. So in this case, we're only going to have one module, and we can write this directly right now. So we're going to read in that file path, and then the type of module that we're going to make is a compute shader. And then again, we make our program. Great. Now we need to attach the shader, but of course, there's only one thing to attach. So this is just a little bit of paper pushing at the moment, a bit of bureaucracy, totally fine. So we will just attach that module that we created. That should be all good. Okay, so we get the link status. Check that. Okay, great. And now we're done. We can delete the module, but as before, there's really only one. So just get rid of that loop. Okay, there it is. That's how we make a compute shader. It's very, very similar to the other stuff. Okay, so now I will close that down and I'll go to my program where those shaders are being created. And that is right down here in Setup OpenGL. As you can see, currently we're just making that blit shader that will put our color buffer on the screen. I'm also going to throw in that compute shader. Okay, I think that's fine. Now, because we just changed a little bit, it's a good idea just to run this and see if any errors come up. Ah, nice, no errors at this point, so I'm happy with that. We can close that down, and I think we're ready to use it. Okay, so this will be happening in the render system. I go to my systems, there's my render system in here. Now we can see that when we create this thing, we do remember the reference to the shader vector. So we've got all our stuff in the update section. See, we're going to draw the screen to the screen, if that makes sense. Now we're going to go raycast. Why did I say raycast? I'm thinking back to the Draw the Turtle challenge, ray trace. Okay, awesome. So what I'm going to do is I'm going to go, okay, use the program. Next thing I'm going to need to do is bind that color buffer so we can write to it. And with binding resources for a compute shader, it's a little more rigorous. It's not quite as simple as, we don't just bind texture like this. So we go GL bind. Okay, so as you can see, we have all this stuff. So the texture unit we're binding texture unit 0. The texture we're binding is the color buffer. Then the level, mipmap level is 0. Is this layered? No, not at all. The layer that we're binding is layer 0. Like I said, this is very explicit, this function call. And then the access will be write only. There's other options like read write, read only, all of that. And then the format, so that will be GL, GBA. Great, right. So our compute shader is bound and ready to go. Our image is bound and ready to be written to. What we do to throw that all off is we go GL dispatch compute, and then we need to put in the number of groups in the X, Y, and Z. So I'm just going to hack this for now. If I go, because we have 640 pixels across, 480 pixels up and down, and we are not going to be doing any 3D work. We have it. And now something needs to happen, because this dispatch compute is like an asynchronous operation. It'll launch that thing. That thing will be working in the background. The GPU is an independent entity to the CPU. So if we just let this thing run right now, we will start drawing the texture when it's partially rendered. As a matter of fact, let's give that a go. I mean, maybe I'm overstating this. Maybe this will actually work. I don't know. See, it seems to be working, but if actually that's okay. That's okay. But I'm still going to do this anyway because it's best practice. So, and maybe we just got lucky with this. So I will insert a memory barrier, and that'll be. So what this is doing is it's basically saying, okay, compute shader, you do your thing, and we will continue when you've finished writing to the image. So again, we'll run that. There we go. Oh yeah, look at that. Performance improved. Okay, so possibly because I didn't have a barrier inserted there, the driver was catching that and doing something else. But there we have it. As you can see, the screen has been written to in a solid color. Now, I've gone on about this a little bit in the past, but let's have a look at setting the workgroup size and all of that correctly. So what I'll do is in the construction, if I go to my render system, I'm also going to store I'm also going to store my workgroup size. Size count, that was it. And in the constructor, I'm also going to take in the window so that I can query it at the time and calculate how many dispatch things to do. Okay, so I'll go to my constructor for my render system. Okay, so let's say we're going with a work group size of 8 in the X and Y dimensions. What I could do is query the size of the window and divide the number of pixels by 8. But, dear listener, the question is, if we have a number that doesn't divide by 8, how do we handle that? So remember that with integer division, it's always flawed, it's always rounded down. So a little trick we can do is the ceiling operation. The way we do that is we add 7, because that's 8 minus 1. So if any of these numbers are 1 or greater under mod 8, then adding 7 will recover another multiple of 8. And in the worst case scenario, yes, you have you go 1 pixel over, then you run a whole other work group. But, I mean, the other work groups are still running at an 8x8 size effectively, and you are covering the whole screen, so all things considered, that's probably a decent approach. So what I can do now is I can go right down here to the dispatch, and instead of hard coding this, I can use the variables. There they are. And of course, I'm going to need to modify my shader so that it knows, because if I run this, okay, first of all, if I run this, it's going to throw an error because I didn't put in the window. So let's fix that up. Let's go put in the window. But now if I run this, it will possibly goof it up. Yeah, look, I mean, it doesn't know that I'm doing 8x8. And so it's just writing this little region of the screen. So I can go to my shader and say, all right, you are expecting to be 8x8. And what that will do is it will adjust the global invocation. There we go. So now we have that. And now look at the performance. This will be slightly thrown off by the OBS recording, but that is at least 1500. And sometimes I see it spiking up a little bit. Okay, so that's how to basically get a compute shader, get it running, and get it running fast. Let's have a look now at some ray tracing. Okay, so I want to have a look at ray tracing because if you know me, my other great love besides APIs is ray tracing. I've done this example a whole bunch of times, but if you bear with me, I will go through it again. So let's say we have a ray, which is mathematically described as an origin position and a direction vector, which is typically normalized, and the reason for that is it makes the reflection calculations a little nicer. Any point on this ray is given by the origin plus a real number parameter t times the direction. So if t is positive, the point will be out here in front of the ray. If t is 0, of course, the point will be at the ray's origin. And if t is negative, it will actually be somewhere behind the viewer, behind the ray. Okay, so let me put the ray equation, and I'm actually going to put my p here. So this is the point of intersection. I want to calculate for a sphere, where is the point of intersection between the ray and the sphere? Okay, so I have the ray equation, and the ray equation tells me that my point is equal to my origin plus t times my direction. And then I have my sphere. Now, a sphere is defined as the locus of a point or the surface of a point such that it is equidistant from the sphere's origin. So let me just put, I have O there, I'll just put A here, or C for center. Okay, so what I have is the distance between the point and the center. Let me square that. So the distance squared equals the radius squared. Okay. And remember that PC is the direction vector from the center to the point. So just for simplicity, I'll say that PC is P minus the center. Okay. And now another thing I'm going to pull in here, this would probably be a great point to say that learning a little bit of math and a little bit of linear algebra will really help. 100%. Not joking. This is super important. There's something called an inner product or a dot product, and it's defined like this. So if I have A dot B, that will be the component-wise sum. So A naught, B naught, A1, B1, and so on. That is also sometimes denoted with this angular bracket notation. That's what I like to use. It's called an inner product, comes from linear algebra. And there's the fact that the inner product squared, sorry, not the inner product squared, the inner product, oh, let me write this. I'm all over the place today. So this is equal to the magnitude of the vector A times the magnitude of the vector B times cosine of the angle between them. Okay, because any two vectors, if we interpret them as coming from the same point, there'll be an angle between those two vectors. Okay, now a corollary of this, I should say, is that the inner product of a vector with itself will be magnitude of A times magnitude of A times cosine of the angle between them, but if I'm measuring something against itself, the angle will be 0. Now cosine of 0 is 1, and any number times itself is the number squared. So the magnitude of a vector squared is given by its dot product with itself. We also have the fact that the dot product is symmetric and linear. So what that means is if I have a real number multiplying a vector, okay, the symmetric part is easy. I can swap the order around in this inner product and it's the same thing. The linear part is a little trickier. So what this means is this splits up, so I can have AV dot W plus U dot W, and I can also pull that scalar multiple out the front. There we go. That's the definition of a linear function. Okay, so let's bring this all together. If I investigate this function here, this PC is given by this expression here. So that is, actually I'll do this. Now this is going to be a little bit messy, but what I'll try to do is I'll try to split up the left side of this inner product. I'm going to run out of space, that's fine. So we'll have okay, so hopefully you can see in moving from this line to this line, I simply broke up the left expression, and if there was any real number multiplier, I pulled it out front. So t is a real number multiplier, I pulled it out. That -1, pulled that out as well. Okay, now I'm going to work on this expression here. So we have u dot u, which is really the magnitude of, sorry, O, not u, magnitude of the origin squared, plus, and then here I'll pull this out. So t times the dot product, origin d, and then, yep, minus that expression there. I'm really hoping some of this is going to cancel out. Let's see. Plus, and then I'll take this, so we'll have t, and just to keep things nice, I'm going to swap that around. So instead of do, I'm going to have od, so it's the same expression. And then if I pull this, I have d dot d, which is the magnitude of d squared. And then I pull that other t out. So I have t squared times that thing. And then now I'll have that expression there. Okay. We'll keep going. So we have minus OC. And then finally those two minuses come out and we have a little messy. That's okay. Okay, so I'll try to bring things together. The goal ultimately is to solve for t. So if I look at this thing, this can be a little intimidating. There's a lot of things going on here, but I need to remember that this, like ray origin, ray direction, these are things that I know. And this is just the dot product between those two. This is just a number for a vector that I know. Totally fine. Okay, so I'm going to group things in terms of coefficients. So if I look at the t squared coefficients, we've just got the magnitude of d squared, and then I'll look at the t coefficient, and around the t coefficient I have 2 times this OD, and then minus 2 times this DC. And I'll just factor around that too, so it'll be 2 times OD minus DC. I think that's right. For the constants, I'm actually going to pull this r squared over to the other side. So I will have, if I look in here, I have this, this O squared minus 2OC. That expression equals 0. Now, I'm going to be a little tricky because when I look at this, I see that I have a common term of d. And so I can imagine swapping this around. So I have negative CD and then bringing it back together. So that would look something like this. If you don't see this straight away, totally fine. I just reckon this will work. Okay. And then if I look at this expression, this looks a little bit like O minus C dot with itself. Because again, maybe this is too basic, but I'll just expand this. So think of this like O minus C dot O minus C. We have O dot O gives us magnitude of O squared. We have O dot negative C. We have negative C dot O gives this negative 2 product here. And then we have negative C dot negative C would give that C squared. Okay, again, the goal is to find the value for the parameter t such that when we step along, we hit the sphere. Now this is a a quadratic equation with the following coefficients. The solution for that would be the standard quadratic equation. And the really big thing to pay attention to is, remember, the quadratic equation will have solutions provided that this expression here, the discriminant, is, I guess, bigger than or equal to 0. And also provided that, we want to get the closer value. So what we'll do is instead of looking at plus or minus, for this case, we'll just go minus. I hope that makes sense. Now, why is this useful? Well, remember as well, not only do we get the intersection point, but with the sphere, the math is so good that we also get the normal vector at that intersection point. So if I have my point of intersection here and my C, then the normal vector will be the direction vector from the center out through that point. So again, my ray's coming in here. There's my incoming ray. I hit there, and I can also calculate the surface normal. So we'll say the normal is, if I go point minus the sphere's center and normalize that, then that is my surface normal as well. So that has definitely been too much talking. Let's get into it. Alrighty, so here we are back in our environment. I'm going to start with the shader. We'll take it from there. So I'll close everything else down. And right up the top here, I'm going to declare some structs. So something you may notice is a little strange is that although all of these attributes are being used, I've also got this padding at the end, which basically is not going to be used. The reason I've got this padding is that the GPU likes the data to be aligned in a certain way. It likes to take in 2 floats at a time, 4 floats at a time. It hates 3. And implicitly, the way it's going to be handling these is it's actually going to be bundling them together into packages of 4 floats. So it's not something to be very aware of at the moment, but it is just a thing. So we've got that sphere. I'm also going to have a ray, which, yeah, it basically just holds those things there. Now, at the moment, I've just got one uniform, that is my color buffer, but I'm also going to take in the camera data as uniforms. Remember I said I got rid of a lot of the stuff, but I kept the camera around. I'm going to keep it there. Great, so those are holding my camera data. In addition, I am also going to do some basic lighting. I think that's fine. Now I'm going to fill this in a second, but for now I'll just leave it. I'm going to have a function which indicates whether a ray has hit a sphere. Okay, if you haven't seen this notation before, in-out is basically treating this variable as a reference. You can sort of think about it like that. There's a little bit more to it, but that's basically how it's going to operate. So like I said, I will leave that function for now. I'll just pop down to the main function and handle setting up the environment. What I'm doing in these early lines is I am working out basically where the current pixel is along the screen as a proportion. If the pixel, for instance, is all the way on the left, this will evaluate to -1. Now, on the other hand, if the pixel is in the center, we'll have 0. And then if we're all the way on the right, that will evaluate to 1. After that, we have a ray. The ray, of course, is going to start from the camera's position. Now, this is a little tricky, a little funky, but the direction we're pointing in will be a linear combination of the camera's fundamental vectors. So if we're right here in the middle, it'll just be the camera's forwards vector. On the other hand, if we were to the left, we would have the camera's forwards vector minus the camera's right vector, and that's a direction pointing to the left. And hopefully you can see that this is very similar to the cube map section where we calculated the pixel going through the screen in the given direction. So that's all set up. What I'm going to do for now is hard code a sphere so we can trace it. Okay, there we have it. I just hard coded some dummy values. Now, what I'm going to do for now is I'll have a t value. It really doesn't matter what that is because we're only dealing with one sphere. And I'll have a color. And I'll replace that down here. So when we write to the screen, we will write the color. So now we can get to writing that sphere to the screen. We'll perform our hit function. There we go. So only the ray which hits the sphere gets a color. Now it's probably a good idea to implement that hit function. So we'll go up above and we will get into it. This is basically setting up the same variables as I was describing in the pen and paper section. We can go ahead and calculate the discriminant of this quadratic equation. And then we have an easy test. If the discriminant is negative, we know that the ray has missed the sphere completely and can simply return. Now here's where I'm going to modify a little bit. It's a very simple function. We could simply return true, but I'm also going to calculate the time on that ray, compare it to the previous hit value. I'm just going to carve off a few edge cases, if that makes sense. So if we were to have multiple spheres, we could potentially get a bunch of hit records. What this t hit less than t is testing is it's testing whether this hit that the ray has performed right now is closer than a possible previous hit. So provided that passes, and then we also want this to be bigger than some number. Remember I was saying that if t is positive, that's out in front of the viewer, whereas if t is negative, it's behind the viewer. This is basically just checking that. So I believe this function is good to go. And it's a great idea just to run this. We won't see anything, but I just want to check at least that we're not getting any errors. Excellent. So we're running that, and there are no errors. We're not going to see anything on screen, and the reason for that is that this is all based around the uniforms, the camera's position. So let's go and modify the camera class or the camera system so that it uploads the camera's data. We'll go to Systems, then Camera System Header, and we'll get that source. Come on, there we go, get them both open. As you can see here, we actually have this already. I'm just going to modify this a little bit. So I'll just, because previously we had multiple shaders that were consuming that uniform. There we go. So again, we have this position, up, right, forwards. This will be all the camera's data that we're sending to the compute shader. And we can go ahead, head to the camera system. And the first thing we'll need to do is in the constructor, we'll need to query the location of all of those shaders. Uniforms, I mean. Excellent. So at this point, we have basically queried everything. We've fetched all those locations. We only need to do that once in the constructor. Now, I'll close that down and I'll go to the update and I'll just go, okay, in here we're doing all of our like detecting key presses, mouse movements, you know, updating the camera. Right down the bottom before we return, I'm going to get the program to upload the camera's data to that compute shader. Again, nothing too crazy. We are simply uploading the data that was being worked on in the camera's update. Let's give that a go. We'll hit play and we'll hope for the best. And there we have it. Look at that. It's a sphere. Now, a few things to note. First of all, if I look at this, the frame rate's actually pretty good. Before we had 1500 frames per second. Now, I mean, yeah, it's taken a little bit of a hit, but it's not doing that bad. Now the reason for this is that typically the by and large, the most common issue with compute shaders is that they get memory bound rather than compute bound. That means, whereas I would like this GPU to be crunching the numbers diligently, it's actually wasting a lot of its time simply writing to the color buffer. Or not that that's a waste of time, you know what I'm saying. Now, second issue, this doesn't look like a sphere to me. So if we go to the shader, the ray tracer, there are two ways to do this. There's the correct way and the also correct way. So the correct way is to get the aspect ratio. Probably a good idea to calculate, to convert that to float so that we don't get any weird results. And then what I'm going to do is I'm going to take my vertical coefficient and I'm going to nerf it a little bit. I'm going to multiply it by the aspect ratio. Okay, so I'll give that a shot. I said I'll give that a shot. And yeah, hopefully you can see that now looks like a sphere. So that's aspect ratio. Now, the also correct way to do it is not to do an aspect ratio, but simply to divide by the larger of the two dimensions, which in this case would be x. There we go. Does the same thing. So which of those do you prefer? I don't know. Personally, I go with the X thing. Issue number 3, I think, is that this doesn't look 3D. I mean, it is 3D. It doesn't look 3D. We can easily make it look 3D. And the way to do that is to apply that directional lighting. So remember I was saying when I explained this on paper that it's very easy to get the normal vector. And actually, that's a great benefit of updating the t value. So I'll just go down to this if statement, and here I will apply lighting. So remember that the normal vector on a sphere is the direction vector from its center to that point on the surface that we hit. So the first thing we'll need is we'll need the 3D point that we hit. Now it's simple enough to get the normal vector, and finally we're going to get the lighting amount. Okay, just using a standard dot product, the same way we would for any sort of diffuse lighting, making sure that doesn't go below 0. So we can now attenuate that color based on the lighting and give that a go, and hopefully this should start looking 3D. I said, there we go. Cool, I mean, yeah, there it is. 3D is nice. We can play around with this a little bit. However you want to do it. It's a sphere. It's 3D. It pops. Okay, so I think that will probably do us for today. And as a matter of fact, that will do us for this series. If you are interested in ray tracing and compute shaders and things, I have a series on ray tracing. Now it does go through this stuff in Python. However, the majority of it is essentially compute shader programming. Well, there is some Python stuff, but hey, you know, if you're really into this stuff, and I've done my job correctly, you should have no problem following along with that. Where things are going from now, thank you by the way, hope you enjoyed the series, hope you had fun. I had a blast setting this up. Where I'm going for the time being is I'm going to be making a few more ray tracing videos on my ray tracing playlists, and then in a month or two I will start my Vulkan series again. So I really hope to see you in the Vulkan series when that pops off. You should have the skills for that now. And yeah, I can't think of anything else to say. Thank you so much for watching. I really do appreciate it. And have a great time. All right, bye. It's not quite perfect, but it's getting there. It's getting there. So potentially I'll be developing this a little bit further. So maybe in another 6 months you'll see another development. But here it is. It's Python. Ray tracing in real time. I thought this was really cool. Thanks for sharing this moment with me, and I'll see you soon.